Hello everyone and welcome to another lecture. Today we will be demonstrating how we can visualize the inverse square law in the case of electrostatics. That is, we'll be taking the Coulomb's law. We'll study the streamlines, that is the field lines between 2-point like objects, that is 2-point charges. So let's get started. First, we want to take our Coulomb's constant to be 1. This is possible if you are not using the SI units, rather working in another unit. So let's try to write k equals to 1, run it. Okay, this is just 1, it's working. And then I want to type 2 charges, that is q1. Okay, let's not, I think q1 is already used, so instead of q, let's try to denote our charges with a very unconventional manner, that is p1. p1 is equals to, let's say, 1, and p2 is just, let's say, 3. So you just put a semicolon over here so that there is no output. And the next thing you can do is that you have to put, in case you want to see the visual representation, you have to put 2 balls. Why? The reason will be clear as we go along this lecture. So to put a ball, first we have to name it. Let's say ball 1, or just in case we don't get confused, we have to type charge 1. To put a ball, first you need to use the graphics command. Inside this graphics you have to type ball, and since you are dealing with 2 dimensions, you have to first specify the ball's origins coordinate. So in this case, this is an ordered pair of x and y. So let's say I want my ball to be on 0, 0, and next thing you have to specify is the radius. I'm taking radius to be 0.1. Let's try to see if this works, and if we run it, you can see a ball like this. And if you want to see the axis, just put this axis command on, and it will show you that the origin is indeed at 0.0 and the radius is indeed 0.1. So this thing works, and let me get rid of these things. Now we have to take another ball, that is our charge 2. So instead of 1, name it as charge 2, but this time I want my ball to be at a point where this is 2, 2, and I take the radius to be the same. And again, if you run it, you will see another ball. So this is working as well. So let's get rid of it by using the semicolon. The next thing you want to do is that you want to write down the force law. So let's say for force, use caps all the way, force 1, this will be equal to, we have to write down the x and the y components respectively. So let's do it. This will be k times p1 times p2, and there will be an x over here. Actually it's x minus 0, but since we're dealing force law for the first ball, but we are not writing the 0 explicitly, so let's keep this x. And in the downstairs you have to type x squared, y squared, and finally you have to put a 3/2 over here. So this is our x component. The y component will be similar, but okay, you have to put a multiplication symbol over here as well. So the y component will be similar. Instead of x in the denominator, it will be a y. So this is our first force law, and this is working nicely. And you can see that this is actually 3 because k equals to 1, p1 equals to 1, p2 equals to 3. So this is just like this, right? Okay, so let's try to put a semicolon. And for force 2, this command will hold, but instead now, since the ball center, that is our charges center, is at 2, 2, that is our charge is placed at 2, 2, so instead of x squared you have to write x minus 2 whole square, and put these braces, and y minus 2 whole square. And similarly over here you have to type in x minus 2, put these braces, for y you have to type y minus 2, and similarly in the denominator. Okay, so we are missing another bracket. As you can see, this is having almost a red sign because we are not enclosing this whole expression. So let's enclose this expression, and I think we're good to go. Yes, this is working perfectly. So the next thing is we have to type something called the net force. Net force, let's define it to be force 1 plus force 2. To see if this is working, we type it, and we can see that Mathematica has actually added this thing component wise, that is a vector addition, right? Okay, so again we're putting a semicolon, and now the final piece of the puzzle is to have a streamline plot of it. And streamline plot in Mathematica only works in 2 dimensions. So let's call it field plot. The reason I'm calling it will be evident very soon, because at first we are not putting those charges in, we'll just see the streamlines. So that command you have to type now is something called a stream plot. And if you want to know what stream plot does, you can see that it generates a stream plot of the vector field Vx and Vy as a function of x and y. So we want to plot this net force thing, right? And then you need to specify the ranges, that is x, and here you have to be a bit careful while you choose the ranges. Sometimes you may get a good graph, sometimes you may get a bad graph, depending on the values you choose for this range, that is for stream plot. So let's take a range from -10 to 10. Oops, there's a dot. And for y we are also taking -10 to 10, and let's try to run it first to see if this is working. And as you can see, it's working pretty nicely, and you can see that there are 2 holes over here. So you can guess that our 2 sources will be here as well, right? So there might be sources over here. So let's try to see whether we are right or wrong. To do that, let's suppress this, and remember that we had our charge 1 and charge 2 over here. So to put them together, we use the trick where we use the command show and we put things together. So this will be our charge 1. Here the order doesn't matter, but still I'm trying to keep one. And finally field plot. Let's try to see what happens. You can see that these are our small charges, sources. Let me just increase the radius a bit. So let's say 0.3, and this is also 0.3. I'll run this whole cell together, and you can see this is a very nice demonstration of our Coulomb's law. Though you might not get the information about the strength of the field, because you see in streamline these arrows, they have almost the same length, so it doesn't tell you that much. So what if you instead use the vector plot thing? Vector plot. Let's try to see how vector plot behaves. You can see that the vector plot doesn't behave that nicely. So what if you took something just the force 1 or force 2? We'll see what happens, because the reason this vector plot is not behaving nicely is either coming from a glitch, because there is just too much numerical thing, or the other thing might be is that these vectors are getting cancelled out very fast. So this graph is actually a glitch, because you can see that there is a vector going through this ball and it doesn't make any sense. So sometimes you have to choose which kind of plotting you want to use. For this method, I think the stream plot is better than using the vector plot thing. So you can actually add some more things, that is, you can add these axes, you set them to be true, then you can add this axis label, you say automatic. You can also change the color using style plot, stream style. Let's stick with, let's just say I want to be light blue or light, I don't know, light green, let's say. And there is another command called performance goal. So what this command does is that it can either generate this very quickly, that is speed, or the quality. Let's go for speed first and see what we get. You can see that the graph is barely visible because I choose a very bad color, light green. So instead of that, let's just choose red, and there you go. So this is what happens when you use the speed. And let's try to see quality. You can see the plot is now a bit better. So this is how you can use Mathematica's different functions to visualize these field lines. Also, this can be done with contour plot, and you can also use a bit dense coding, that is a bit high level coding, to use that vector plot to your advantage. So for this lecture, this will be it. And notice that we could have also done this thing in terms of the Newton's law of gravitation, where we can take this masses, and since it's an attractive force, we can put in a minus sign over here. For example, I can use this minus sign in force 1, let's say. So this means one of the charges is negative, right? And let's try to see, let's try to run this whole thing. And as you can see, this is a very, very accurate representation of our electrical field lines. But notice that there might be little glitches. For example, over here, that this line is actually crossing this charge, which is not true. So this is a very nice thing to add in Mathematica, that you can actually put this charges over there, and you are seeing these field lines that you are often taught in textbooks. And I have to add that the reason you are seeing this this line, for example, if you follow my cursor, because here I am embedding two images. So to get rid of it, you have to write another sophisticated code, but I won't go into that today. So let's try to see what happens if two of these charges are so this is, one of this is positive, another one is negative, right? But let's take both of them to be negative and see what happens. Again, you can see, as you would expect, that's all the fields line, that is all the streamlines are coming in, but around these 2 points they are kind of repulsing, or you know, they are just rippling each other. And again, if you just take this one to be positive and this one to be negative, this is the kind of streamline plot you would get. Or again, you just make the force positive again, this is the thing you are getting, right? So this will be it for today, and you can actually play around with it. So that will be it for today, and I'll see you guys on the next lecture. Thank you.